Hi, folks. Welcome to this midterm review for ISBT211 instrumentation and measurement. Again, we're trying to take this course hybrid so that all of the classroom presentations are here online inside Canvas. So this will be our first attempt at taking our second exam. We're going to take our second exam live during what is normally laboratory sessions. So it's scheduled for this Wednesday at 2 p.m. For exam number 2. And it will be covering all the material that we've had since exam 1. It's all enumerated on side of our Canvas website. So I'm going to push the button here. Let me get some buttons pressed here and walk over to our Canvas site. So here we are inside Canvas. Again, this has not changed. This is sort of the same thing we've been looking at the same time here. Let me push some more buttons here. Here we go. Fantastic. So here we are. This is the stuff that we've had for exam 1. Obviously, exam 2 starts with Prezi presentation number 7 through 12, actually. And remember, 12 includes 10A. I mentioned that we were going to circle back after talking about the basics of acids and bases as models. We're going to talk about how to measure acids and bases. We're going to do so in a presentation called 10A pH measurement, which is here. So hopefully you've had a chance to take a look at that here on Canvas. It's down here. Here's the Prezi as before. So I've kept the same pattern of providing the actual Prezi, if that's useful for you studying wise. And then down here is actually, in addition to the actual Prezi link as before, and the PDF, here's my presentation of it online. So that's so what's being covered. It's all here, obviously, instrumentation and noise, concentration modules, strain, acids and bases. And then our first 2 force fields gravity and force fields electric. And then again, circling back to do pH measurement specifically. There's actually another force field we're going to be talking about, which is going to be covered in the last 3 weeks of class, which we're in now, which is force fields magnetism. And of course, as you guys already know, because we've started to talk about the laboratory sessions for the last few modules of the course, and then will be part of the final exam, that is electromagnetic fields. So we need a little bit of magnetism to be able to put those two together and get an idea what's going on. Down here along the bottom of our Canvas site, we don't have many homework assignments for the second part of the course, so just numbers 5, 6, and 7. I've gone ahead and posted the midterm review. I didn't do a very good job of keeping it the same pattern as the first one, so I'm calling it midterm 2. Here's the review. I'm gonna go ahead and push this button here and get a look at it. So here's what it looks like if you download this thing in PDF. It's very similar to our first review. This is something that I would probably have gone over in class in much the same way. We're still talking about our terms and concepts that we've been talking about all semester. How do data, information, and knowledge weave together with the transducer and model? How do we go about doing that? The things that we have not talked about yet on the exam start with strain gauges. And again, all of these particular topics, again, the exam is open notes, open everything, just not open partner. So hopefully you have some definitions for what all these strain gauge terms means. We talked about signals and noise. We had a laboratory session on both strain gauges and signal to noise using LabVIEW, if you recall. So we talked about the signal to noise ratio. We talked about where noise comes from. And we specifically talked about how we can make the signal to noise ratio better. How can we minimize the noise and how can we maximize the signal? We talked about physical shielding, modulation, and averaging. And then we moved on to these models of concentration, which we definitely use in the lab lots and lots of times. We talked about concentration. Thankfully, these are things that we use in other classes a lot. So hopefully it's not too amazingly new, especially in the biology side or the wet side of ISBT. I know you find folks have been talking about percent concentration for quite some time. So again, we talked about percent concentration as a model. And then for those of you who have been taking classes in chemistry or have had chemistry classes in high school, we know that the chemists most often use molarity to talk specifically about moles or number of molecules as opposed to grams versus volume, which is much easier to talk about and more convenient inside the bio laboratories. We then moved on to acids and bases. Why are they so important in biology and life processes? It sort of makes sense that we need to have a handle on what acids and bases are and what they do. We're most definitely checking the pH quite a number of times inside the bio laboratories, especially in Marcia and Dr. Jones's class. So we covered the autodissociation of water. Why do we have acids and bases in the first place? We talked a little bit about the equilibrium constant K, how that's actually formed. And then we talked about, oh, by the way, one of the definitions of an acid and a base, the Brownstedt-Lowry version is that acids donate an extra proton or an H plus ion, and bases accept or soak up extra H plus ions, which makes solutions acidic and basic based on their properties. We talked about models of pH, the little power function of the small p and what that little p means. And again, we learned that that means that you take the p of anything, any value, any variable, and you get the p of something. In this case, if you're taking the p of the hydrogen ion concentration, we call that the pH. That's the one that we use most often. It is simply the negative of the log. That's the logarithm base 10 function on your calculator. Simply take the value, press the log button, take the negative, switch the sign, and you get the pH. So again, for actual pH, it looks like this. And this is the buffer equation, the Henderson-Hasselbalch equation we talked about in one of our homework assignments that allows you to calculate the pH of a buffered solution based on the pKa of an acid and the relative concentrations of the acid form and the base form. So I'm not going to be asking you too amazingly detailed conversation questions about that on the exam, but at least I'd like you to know what they are and how we go about calculating them. We then are talking about our two primary force fields for the exam. The first one being gravitational field, the second one being electric field. I'd like you to sort of recall what the similarities and the differences are. Remember that gravitational field has an equation. The equation looks like this guy over here, where the force equals the gravitational constant, capital G, and then we multiply that by the product of the masses and divide it by the product of the radiuses, or the single radius, which of course what gets it squared. And as you guys know, if we go ahead and put all of these values in for Earth, it happens to fall out and be a very, very common number of 9.81. At least that's the average value that we typically use when we're doing physics equations. Electric field wise, about the only difference is we're still talking about two different particles, except for this time, rather than having two particles of mass, which are identical, in as much as they both attract the other masses towards it, we know in electrical charges we have opposites. We have antimatter. We have anti-charge, I guess is our anti-particles. We have positive protons. We have negative electrons. And again, as we saw in the Prezi and we talked about in class, the way that we describe the electric field of a proton is we talk about the field lines coming out of the positive charge, and we talk about the electric field lines going into the negative charge. It's just how they happen to be described. And when we do that, we then can talk about lining up all these positive charges in a particular magnetic bar. Or I said magnetic, an electric bar, and we can line up all the negative charges in a different polarization of an electric bar, and that allows us to make an electric field between a difference between the positive charges and the negative charges. And if we plop an additional positive charge, we know that that positive charge is attracted to the negative or pushed away from the positive. And then the opposite is true for negatives, where they're attracted to the positive and they're pushed away to the negatives. So nothing too terrible. That's the end of the review session and the review paper. A few equations. Oh, by the way, the force that we have on an electric field is simply the amount or the size of the charge, which in physics is designated as a Q, times the strength of the field, which happens to be designated as a capital E for electric fields. So force equals Q times E. And what I'm hoping that you understand model-wise is that's very, very similar to up here in gravitational field, where force equals mass times g, little g, the acceleration inside the field, which again is just this giant equation that has been put in some constants and some average values for the size of the Earth, both in its mass and its radius. So they have very, very similar construction on how these things work. The push or the pull on charge is simply the charge times the strength of the field, and the push or the pull in gravity is simply the size of the mass times the field. They're pretty much the same. So with that, I'm going to go back over here to me, the front pocket over here. So I'm expecting that folks will take exam 2 in the laboratory on Wednesday at 2 o'clock. If it's not the normal time that you have lab, then of course we can stop by on Thursday at 11 and take it. I know we have a few folks who are on the soccer team and they're traveling for A10s. So if it turns out that we don't take it this week, we'll get to it next week. So with that, I hope this experiment with the hybrid is working out, and I'll see you on Wednesday for exam 2. I'll press the button here. Thanks so much. See ya.